Welcome. My name is Brian Sam-Bodden. I am a developer advocate with Redis. Formerly, I used to be a consultant, so I worked on pretty much every Java technology that you can imagine. I also did a lot of Ruby because that's where the cool kids were at some point. In the last few years, I really got into data science. I'm doing a master's in data science at this ripe old age, and it's been a lot of fun. And that actually has given me an avenue to see how I can do those things with Java. And also at the same time, my company has a add-on to Redis that allows you to do some of these things. So I kind of ended up here by that confluence of factors. And obviously, this is about Spring and Redis and how to do things that you might not think were possible with Spring and Redis. So that's my email and my Twitter handle. And my GitHub account. And that's me before the pandemic thinking it was just gonna be like a couple weeks. And now this is me 30 pounds later. So it's work in progress, don't judge. All right, so the quick story here, the why, the what, and the how. Vector similarity search, it's basically popping up everywhere because our data has changed radically. We used to try to always organize the data because it was significantly smaller amounts of data. And now the data, even if it's a textual form or column-based, you can't really guarantee those things, and the pre-processing and cleaning of the data sometimes is too expensive. Just the fact that you would have to hire a whole team to clean the data prevents you from actually doing something actionable with the data in a fair amount of time. So what are we going to be talking about? Vector databases, vector search engines, and vector similarity search. And this is one potential answer to the question of how do you deal with all this unstructured data? And by unstructured data, I mean images, video, blobs of text, DNA sequences. It doesn't really matter. It's typically highly dimensional data that would be too hard to deal with in a SQL environment or a NoSQL environment. Given a NoSQL environment is more apt to store that data than a SQL environment. And the solution I'm going to propose today, it's Redis. Let me see a show of hands. How many of you have used Redis before? All right, so if I say Redis, what word comes to mind? Cache, yes. So I've been tasked with the mission of convince people that Redis, it's first of all a memory-first database that happens to be a multi-model database in that it's extensible. So you can basically mold Redis to handle different data loads and different, it's a computing engine too, because the idea of data locality, bringing the computation to where the data is, it's been around forever, and we know that we can gain a lot from it. How many of you had to resort at some point to a store procedure in a SQL database to save your skin? And people used to malign store procedures, be like, oh yeah, because it's PL SQL or one of those dialects. But they were significantly faster than anything you can write client-side because you have to take all the data to where the computation was. So with Redis, we're going to exploit the possibility that the data is already in Redis or that you put it in Redis so we can do things with that data locally. I forgot all about those. So the data balance. I was talking about this. Some data suggests that 80% of the data generated right now is unstructured, and that percentage is growing over time. So the amount of structured data that we're going to have is really just the tip of the iceberg that allows you to maybe find some bearing to where to look into that unstructured data. So the consequence of this and of all the techniques that I'm going to talk about, it's that people are expecting search experiences that are much more powerful. They are expecting to have a search experience that deals with this multidimensional data and that it takes into account not only the actual values of those data, but the semantic meaning of some blob of data. And the two fields that are pretty closely related here that can be implemented with the techniques that we're going to be looking at today are recommendation engines, and obviously the similarity search it's something that happens at the end of any process where you're dealing with vectorized data. You're trying to find, either you try to cluster things, or you try to find in the neighborhood of something of interest the things that are in that multidimensional space. And this will make sense in a second. So searching, we have high expectations. We have things like natural language searches where you would say something like in the top example, it's like red tops under 20. It's not mentioning dollars. It's not mentioning anything else other than tops too, which it's a very loose definition of that. But given a large enough corpus of data to train that, the meaning of a red top under 20 can be inferred from that data. You have visual search, a very popular one. It's Pinterest. So you can go and take a picture of something and say, here's something that matches the decor of that, or the fabric, or things of that sort. And then, of course, we have the old school recommenders. Old school, I'm talking about, 15 years. Amazon recommendations, Netflix recommendations. You guys remember the Netflix prize? Like, was it 2009? I thought I was going to become a millionaire, and then I realized I knew nothing about data science. So, all this unstructured data has to be put in a format that it's easy to manipulate in a mathematical matrix operation type of way. And we call that data vectors. And it's not like the vectors from physics where you have a direction in a dimension or a momentum or something like that. These vectors are really just arrays of numbers, typically flat. Can there be multidimensional vectors that are like matrices and stuff like that? Yes. But most of our machine learning models do very interesting things with this unstructured data, and at some point in that network of values, there's going to be a flat layer that eventually pipes down to some kind of classifier where you would say, oh yeah, this is a dog, a cat, a horse, or whatever. But those vectors, people realize that they could take that and then do a lot of interesting calculations with those. One of them being similarity. In a multidimensional space, does this vector, it's near this vector, and is it pointing in the same direction, and is it about the same size? And it turns out that based on the AI model that you use, you can find really interesting correlations between that data. So let's talk about storing and creating vectors. So again, there's a numerical representation of something in n-dimensional space. Why n-dimensional? For example, textual data, it could be things like categorizations that come out of the text. It could be a range of colors or a palette or things of that sort. So it's from fine-grained values to coarse-grained values. A vector could represent features of that data at different levels of granularity. So for example, you've probably seen the pretty scary CNN convolutional networks in between images, where it's basically extracting features from an image. And some things are recognizable, like, oh, here, eyebrows and noses and lips and mouth and chins and stuff like that. But then you start seeing things that will horrify you, but they're actual features that can be compared across a universe of, let's say, faces. And those are the unexpected features that machine learning models get out of data that we could have not engineered ourselves. So vectors represent a lot of stuff about something, and they are typically represented as some sort of array, a rate of probably floating point numbers. So let's picture a few visually. Imagine that you have a vector for a queen, and a vector for a king, and a woman, and a man, and you can see that they are kind of in the same plane. So the idea is that you will have some sort of hyperplane where things that are similar by a certain number of features will be in the same hyperplane. So you have here semantic relationships and also syntactic relationships. So for example, between big and biggest, you can see that the magnitude of biggest, it's the tip of that vector, it's farther out than big. Here's a few others that I found online that are pretty interesting. So for example, you can see that I just lost my mic. the relationship between countries and capitals, they're all oriented the same way. But they're in different parts of that 3D space in this case. But that 3D space could be, that part of the hyperplane could represent something like political instability, other things. Of course, after 3 dimensions, we can't really visualize it really well, but imagine if you could, all these different features of the data represent places in this multidimensional space. So somebody took the initiative to actually color code a encoding vector or a feature vector from a word classifier. And you can see that the values between man and woman, the colors are kind of lining up somewhat, but also between king and man. So that's how, and this is actually a very simple visualization. They just basically gave a range of colors to the float numbers from 0 to 1 in there. But you can start seeing that there's some similarity here and some correlations between the concepts in here that make sense. So how do we go about generating these vectors? So the generation of a vector is typically called an embedding. And that's the data science word for that. People also say vectorization or the generation of embedding vectors. So you can get as wordy as you want with that. I call them vectors because it's the easiest concept to come across. So typically, the steps to create a vector embedding for a piece of multidimensional data, it's choosing an embedding method, then cleaning and pre-processing the data as needed, and then train the embedding model with some target data that makes sense for your domain, and then you generate the embeddings. Typically, like I said, the networks are classifiers of some sort. So at the end, they tell you something about the class of the thing you're trying to deal with. So like I said before, it could be dogs, cats, horses, or something like that. So you don't want that. What you want is the layers before that have this multidimensional data encoded in a way that you probably don't understand, and none of us can. To this date, we're basically going after the concept of explainable AI. But it's still pretty hard to figure out what's going on inside of a very deep neural network. So in the last 10 years, vision models have skyrocketed in their performance. You have YOLO and a whole different families of vision models that can now really beat humans at classifying things and detecting things. Obviously, everybody here, I actually use GTP4 to actually help me with some of the concepts for the presentation. I'm like, can you explain that to me like I'm a 5-year-old? And I'm like, oh. And then, can you explain to me like I'm a 10-year-old? So this stuff, it's pretty amazing. It's mind-blowing. And we still don't understand how it gets to that. We understand the processes, intermediate processes, but some of the intermediate data, it's still baffling to most computer scientists. So these large language models, when it comes to textual data, they're amazing at generating things that you can now use, the vectors that you can now use to compare things that were incomparable before. And again, it's all about semantics, capturing the meaning of something in a context. And vector similarity becomes basically a very simple tool once you have these powerfully created embeddings. So before, we had vector similarities have been around for eons, but our vectors were crap. We couldn't generate vectors that carry enough information and meaning about the data. But now we can. There's also an ever-growing collection of AI models, pre-trained and scriptable, tunable, that you can actually use in your code today to do all kinds of things, from sentiment analysis to creating chatbots, to doing amazing things with vision models, with audio. Anybody has tried Google's hum to search, where you can hum a melody and it will basically tell you what the song is? So, before that, I remember when Shazam came out, I'm like, wow, this is amazing. It's like, I just really wanted to know how they actually did something like that. In Shazam, not that difficult with the stuff that we have right now. You can build your own Shazam, at home in a few lines of Python. I'm trying to change that too. But now you can do things like that. This home to search stuff, it's just amazing. And it's all pre-trained models that basically know, for example, obviously somebody had to create some data about first a transformer or turning a song into a humming set of rhythms. And then use that to train that with the classifier saying this is the song. And then do it over and over and over again over a very large collection of music elements. So for sentences too, there's a sentence sentence pre-trained models called SBERT. And there's a whole family of models in there that you can actually plug into your Java code. I'll show you how to do that in a second. But these are pre-trained models that are trained on specific corpuses of data. It could be medical data, it could be legal data, it could be general, like Wikipedia type of data. So they're pretty effective. And typically the process, it's for you either to train it with your own data or extend the training with your own data or play around with the different models to see which one comes up with the best results that you can possibly get. And it's a never-ending competition in the machine learning world now to beat other models. So it's become almost like a space race. Models keep on beating models, and they publish a paper, and you keep on fighting each other. So it's so far to our benefit, unless the whole Skynet thing happens, and then I'll be in the resistance with you guys. So once again, for vectorization, there is, this isn't a typical model for vision. You have convolutions that basically scan through the image to basically get features out at different sizes and resolutions, orientations, and things like that. And at some point, you're going to have some pooling in flat layers of that network. And those flat layers is where typically you will tap in and say, oh, that's my embedding. So rather than go all the way out to the output, you say, oh, I want to get one of these intermediate layers that have very incredible packed information for me to use. All right, so let's vectorize something first so you can see how easy it is with Java. Oh, yeah, I forgot. One more slide before we vectorize it so you know what I'm talking about. So there's several frameworks in Java to do machine learning now, but they were all kind of disconnected and floating around. And as a few years, DJL has emerged as the one that's kind of basically wrapping all the other models in systems around. So this is more like a syntactic sugar in a lot of the legwork done for you to basically give you a framework for machine learning that basically can abstract PyTorch. So you might be doing it in Java, but the model that is running under the covers is a PyTorch model or an MXNet model or a TensorFlow model or an Onyx script. So it's pretty amazing that I didn't know about this for a long time, because the moment I found it, I was like, finally, a portable way to basically do data science in the Java platform. And one of the things that the Python world lacks, it's the knowledge of how to distribute and scale things. Most data scientists in the Python world do things in a Jupyter notebook. So they do things top to bottom, like we used to write Hello World Java programs, in 1995, and then they hand out to a machine learning engineer. So they have two categories. There's the data scientist and the machine learning engineer. And in my mind, that's a silly division. It's like when we used to have only server-side developers and only client-side developers. If you're only one of those two, at some point you're going to be out of the job. So, and then remember, we came out with the full stack developer to say, yeah, just a developer. You don't have to say full stack. It should just be developer. So this framework really wraps seamlessly those systems, and it takes into account things like whether you have GPUs and CPUs and all that stuff really well. It also taps into the model zoos from a lot of the other communities. So like you can tap into Hugging Face, into PyTorch models, into TensorFlow, Hub, and use models from there by using the URL of the model. Some of them have to be ported somehow to DJL, but some others can be used as they are. All right, so now let me do a quick demo here. So I'm going to do a bunch of little demos and then a couple big ones. Okay, so here's my little vectorizer model. So for this one, I'm going to do first a words. Which one did I want to do? Words embeddings test. So here. So again, this is an example of how I can use multiple different transformers. So I get to choose from that list in there. And that's just a small list. Some of them are coming from SBERT, which is sentence transformers. And some of them are coming from this VOCA transformers. And you can see here that I created a list of words. Sentence encoders can encode sentences or words. Obviously, the words is going to be one encoding per word, and the sentences is going to be one encoding per word in the sentence, or not counting stop words and things of that sort. So in here, notice that I have a map of some properties, the length of the encoding that I want, the maximum length. And here I'm using something called the Hugging Face Tokenizer. This is a wrapper, even a higher level wrapper that says, okay, I know you're trying to basically tokenize something. So given a transformer, in this case, I'm using the last one in the list, which is the Distilibird. And then I'm going to take my sentences, create a stream, and map them using the tokenizer encode method. And then I'm going to collect that to a list, and then I'm just going to print it. So if I, make sure I run the right one. What did you do, Brian? It's an all run configuration. There we go. So there is my embeddings. Obviously, you want to transform this further to, for example, a byte array at the end of the day. Right now, I just have an array of floats or integers. Right now, these are integers or longs just because it's a word embedding model or a sentence embedding model. So that's how easy it is to use stuff from the Python world that you needed to learn Python and all that stuff, and now you can do it from Java. Not a problem. All right. So, similarity. Finding similarity between those vectors in this n-dimensional space. One of the most common measures to do that, it's cosine similarity. So you can see the three figures that I have in here. The similar vectors have an angle close to 0 and a cosine close to 1. The orthogonal vectors, which means that they have nothing to do with each other. This is like what most marriages look like, orthogonal vectors. Those are the ones I think that survive pretty well, I hear. And then the opposite vectors, when you have complete opposite concepts, obviously one is pointing that way and the other one is pointing that way. So that makes sense. And all this, the measure of that angle and the measure of the cosine can be used to determine this. But now in here, we're doing it in 2D space. Now imagine this in a space that has many, many more dimensions. Here's an example of embedding movies in a 2D space. So you have something like, for example, here's blockbusters on one axle, art house films, adult films, children films. Not adult films, just like for grown-ups. Come on, guys, seriously. So again, anything that you can think that can be categorized manually by doing feature engineering, or by the features being organically extracted from the data by a machine learning model. So another pretty cool example too with vectors is that vectors, you can perform arithmetic on the vectors. So in this typical example, depending on the encoding that you're using, you could say that king minus man plus woman, it's close to queen in that n-dimensional space. And that is, when I saw that image, I read one of the papers on Word2Vect a while back, and I was like, how did I not know this for the last 10, 15 years? So this stuff, it really basically resonates with developers. If you have, that a bit of inclination to read some of these papers, you're like, oh, we can do that. And the fact that we don't have our act together in the Java community yet, we're getting there. Yeah, the Python guys kind of surpassed us in popularity just because of this stuff. So we can still catch up. So how many of you have used Redis before? Let me see a show of hands. So just a few. Okay. So let me tell you quickly what Redis is and what it's not. So I'm doing this. When you are of Latin descent, your hands move like an Italian's hands. So I'm going to be knocking this microphone off a lot. So Redis stands from Remote Dictionary Server. So initially it was just a distributed system where you can basically put data structures. The initial data structure was the simplest thing, name value pair. That's in Redis, the architecture led it to be used very commonly as a cache because it's one of the fastest caching engines out there. But in reality, Redis was meant to be, well, initially it was meant to be a cache. I mean, no arguing that. But then the architecture lent it to become an in-memory first database. And I say in-memory first because nowadays the line between hard disk and memory, it's slowly getting blurred. And at some point, it's not going to matter. When you say in-memory versus on disk, people are going to say like, yeah, those are concepts from like 50 years ago. So this is where we're going. Everything's going to be in memory. And right now, basically, our limitations are how much of that memory can you afford right now. But Redis has become the band-aid for bad architecture too. Every time there's a system that's underperforming, they say throw Redis in front of it, which I wouldn't recommend that from an architectural point of view. Find the root cause of the problem. But if you're in a bind, that's typically what Redis ends up doing for you. So it's in memory first, and it's optionally persistent. Most people think that, oh, Redis, once I pull the plug, my data is gone. No, it's like Cassandra. It has basically a log-style system where basically every transaction gets written to a log, in that there's also a binary image that log gets played against to basically, bring the binary image to the current state of the database. There's a bunch of data structures in there: strings, bitmaps, bit fields, hashes, lists, sets, sorted sets, geoindexes, hyperlog log, can you say that twice, and streams. The streams are kind of like Kafka streams, but simpler for smaller type of streaming-like activities. But the hashes, it's typically the workhorse when it comes to object-oriented languages because they map really well to objects. There's also an extension ecosystem. And the one that I'm talking about today, it's Redis Search, the one in the middle top, and a little bit of Redis JSON. And the idea here is that you can basically add modules to Redis that they add new data structures, and they add new operations on those data structures. So one of the ones that we have is Redis Search, which is basically a full-blown Lucene-like search engine that allows you to do searches on the Redis side of the fence. And we have packaged those source available modules in something called Redis Stack, which basically you can just do a download from Docker and just get a Redis Stack image that has these 5 modules in here, which are the JSON search, the graph database. So there's also a graph module in Redis, which gives you a Neo4j-like database. It's less capacity, but way faster. Time series and Bloom, which are Bloom filters and other probabilistic data structures. So I'm not going to do the demo of Redis, the database, because I want to get to the meat and potatoes. But again, Redis, it's at the command line level, like using Telnet back in the day. You basically say command for Redis against a data structure, passing some data payload, and you can add things to a hash, remove things from a hash, add things to a JSON document, remove things from a JSON document, and with the search module, you can basically query indexes. And you create indices from specific data in hashes or JSON documents. So vector similarity in Redis. How did we get here? Well, Redis is also very good at storing blobs of data. And the typical embedding, the most efficient encoding for an embedding in Java, it's a byte array. And Redis is pretty good at storing those. So the team that works on the search engine said, well, why don't we just add a vector type field that can be indexed, and then we can do similarity searches against blobs of binary data in hashes or JSON documents. And that's how we end up with Redis as a vector database. So, and again, this is going back to the whole models too, and picking the right models to create your embeddings. As long as you can end up with a byte array, you can put it in Redis, and the vector type field in the search engine can do similarity search by different measures. So you can have music, video, images, also specific models that are fine-tuned for things. So today we're going to use one for faces. So you can use a model for faces, poses, basically sentiment analysis and emotions. So happy face, sad face, things of that sort. So the fun thing here is that there's so many models out there right now that it's like using Legos. You can really stack them in interesting ways to get what you need. All right, so for vector similarity in Redis, you need to index and query the vector data stored in blobs. The blobs are byte arrays, and they could be in two different data structures, hashes or JSON. There's three distant metrics: Euclidean distance, which is basically the straightforward, how far is that thing from here if I throw a straight line to it. There's an internal product and the cosine similarity. And there's two indexing methods. There's the HNSW, which is small world. It creates basically a map, kind of a graph. An optimized graph to reach the position of the other vector you're trying to compare. And there's also flat, which is kind of like a brute force approach. And you can combine, the cool thing about this is that you can combine the vector similarity searches with regular searches. So you can say, I want to find all the JSON documents where the category is, I don't know, pantaloons from the 1800s, and where this vector similarity is, a certain degree. So you can really mix and match like you would do in any kind of a query environment. And that could be geo information. It could be tags, which are exact string values. It could be free-form text, or it could be numeric values. So one of the things that jumped to me when I was trying to build demos with our stuff, it's that using the lower level clients was very non-intuitive for programmers. So there is a project in Spring Data called Spring Data Redis that basically adds the capability of mapping Spring entities to Redis hashes. And also adds secondary indexing by using some of Redis built-in data structures like sets and things like that sort. So you could say, for example, do the basic find by first name in Spring, or find by first and last name. But anything more complex than that, you were out of luck. So what I did is I extended Spring Data Redis. And this was basically what I call conference-driven development. I said, what can I show that wouldn't be embarrassing for me to build live on stage? So I had to basically take a lot of that CRUD and ceremony that had to be done with lower level clients and do it in a Spring way, declarative way, annotation-driven way that would make it easier. So I ended up with something called Redis Ohm Spring. And we have our own library for pretty much each one of the major languages right now. And I'm the one that maintains the Spring one. So it's a multi-model object mapping and querying. It extends Spring Data Redis, and it uses Redis, which is one of the lower level clients. Worst name, if you try to Google anything, you're gonna get Obi-Wan, Padawans, all that stuff before you get to the information about what you're looking for. So the idea is that you have, for example, this one, Redis hash, it's the Spring Data Redis annotation, But when you use it with Redis Ohm, now you get searching capabilities too by adding indexes and things of that sort. Also, the queries are much more powerful, so you can, the auto-generated method-driven queries too work pretty much as close to JPA as possible. Here's an example of a Redis hash that has an index field. And when you do an index field, you can do now, for example, find by first name, but rather than using a set to do a reverse lookup now, it uses a search engine. So now you have a real search engine behind Redis map data in Spring. Here's another example where some of the other stuff comes into play. That searchable annotation near the top below ID allows you to do a full text search on that field. So that could be a blob of text, and you can do a full text search on it. Below that, there's a Bloom filter, which basically allows you to test for membership in a very fast way in a fixed amount of memory. So now you can say, has this email been taken? Just by adding that Bloom annotation. And it does this. Obviously, there's a very minute risk that you get a false negative. But in most cases, this is acceptable when you're basically having your system bombarded by people, and you can say, oh, you already have an account, that email has been taken, move on, move on, move on, without wasting CPU cycles. Notice that there's also audit fields like you have in Spring JPA facilities, created, last modified, all that stuff is available now. Now, yes? Well, yes. So in that case, you will go down and verify. So that's typically what you do. You're like, oh, okay. Yeah. So let me show you a quick demo of Spring Redis Ohm Spring with this to-dos application that I put together. So here I have this to-do application. Let me show you the application main file. You can see that it's just a Spring Boot application, and it has the enable Redis document repositories. Below, I have a command line runner where I can actually load a bunch of data if I need to. And then that's it. It has just the, what do you call this stuff? The Spring Doc. What was the name of it before? Yes. Yeah, so I added one of those in there. But as you can see, it's a normal, standard garden variety Spring application. Here's our to-do model. In this one, it's actually being mapped to a document. So this one will use the Redis JSON data structure to store the values of the object. Again, you have an ID that becomes a ULID, setters, getters, all that stuff. But all those fields that are marked with index, if there's any marked with index, they become part of the search engine in index. There's also your normal garden variety repository. And this one is just extends CRUD repository, and then you get all this stuff for free. So now let me go ahead and run this. Oh, it's funny, the colors don't change in the terminal. But so in here, let me go and go to localhost 8080. And here is, I wrote a React front end for this, but I normally have now HTMX interfaces, which is just a single HTML page, no more JavaScript, or very little. So and now if we go and look at Redis Insight, you can see here that now we have two JSON documents that are stored in the database. So that's what Redis Ohm Spring does for you. So now let's move on to, and again, you can basically use it like you use JPA. It's just faster. All right, let me stop this, and now let's get into Similarity. Okay, so the next demo I'm going to show you now introduces Redis in the context of vectorizing and indexing vectorized data. So we're going to do a facial similarity search. And to do that first, I have to show you some of the processes that have to go through before I basically bolt that onto the application. And I'm going to do it in plain Java code first so you can see then what the framework is doing on your behalf. So one example here I took, and this is from one of the examples in the framework. This is supposed to be the world's largest selfie. I don't know if this is a true claim, but I want to show you how to detect and extract faces from it. So back to that same demo that I had before, my vectorizer project, I have a retina face detection, which came straight from DJL, but I added some extra stuff to it. And if you see, the largest selfie image is right here. And let me walk you through the code so you can see what you could do in plain Java without Spring in your Java applications. So most vision models have some prerequisites of the size of the images, the density of the information in the images, the DPIs, all that stuff. So these are ones that actually work with this specific model. And here's the largest selfie. It's a JPEG. I'm loading that JPEG into this image object, which this is from DJL. And then I have this face detection translator uses some of these models to basically translate the images into the right format. But now below here, I have that criteria of how to find a model in the model zoo. So in my case, I just said, hey, just use this one exactly. But you can say, find me a face detection model that can handle these resolutions, for example. And it's trained specifically for facial recognition, not just for general images. So it's almost like a query to find the right model too. Obviously, you will do that in development, and then eventually you will probably co-locate your model with your application because it would have to go out of your network to basically get it. But so in here, I'm using the retina face model, plugging the translator that I created. They throw in a nice progress bar for free, and I want to use PyTorch as the engine under the covers. And then all I need to do is load the model in a try with resources, and then predict. Get a new predictor and predict with that predictor passing an image. And then I'm saving the bounding box image, which it's a method that I wrote down below that basically, the framework does all this. You just basically can get the bounding box and apply it, the bounding box down here. There's a draw bounding boxes. It's not like I wrote a bunch of code to do this. And I extracted the first face. So typically, a face detection model would basically sort the images in terms of the most prominent ones. So typically the biggest face in the picture. When it's all my family, since I have a big head, it will be me. You're not supposed to laugh at that, man. Seriously. All right, so let me run this so you can see what we get. Oh, sorry. So it's doing its thing. And in this case, I think it downloaded the model again because I had it deleted. And it's finished doing what it was doing. So now in my target output now, I have first the first face detected, which if you remember the largest selfie, this is the actual person, I think, holding the camera. And then the retina face detected image shows you basically all the faces that it detected. And you can see based on resolution where the model basically says, I don't know what these 4 pixels are. But so there's still an element where a human will say, oh, there's faces back there. And some of the best models are like, I can't tell you. So, and I think I set it to 85% detection. So if it's the 85% accuracy, give me those faces only. So maybe if I lower that down, it would give me some more in the smaller part of the equation here. All right, so that's how to do face detection extraction. And now for this celebrity match demo, what I did, it's in a lot of parts of the framework, I gave sensible defaults to things. So I have categories, basically. You're trying to embed a face, create an embedding for a face or a general image or a blob of text, and I put the most current general models in there to do this. But they're all configurable, so you can basically go to the applications or property and plug in the models and the parameters that you need for your application. So what the model does, it's creates a celebrity domain that is mapped to Redis hashes, uses the data repositories to basically save those objects. The data comes from a CSV file and also a bunch of images that are mapped to those rows in that CSV file. I use the index annotation from Redis Ohm Spring to annotate the field that's going to be the byte array that represents the embedding. And then I use the vectorized annotation to tell the framework to get the image from a URL in the model and create the embedding and put it in that other byte array. So you can basically get a destination for the vector created. And then in the demo, it's a Spring Web HTMX application where you can upload an image and it will detect the faces, extract them, and create an embedding for the input image, and then do vector similarity search against the database. Now, this demo, it's a little slower than most other demos because I am accounting for them potentially sending me multiple faces. And like we did in the example before, I will find the most prominent one and search for that face. Most demos of this kind assume that it's only one portrait picture of somebody. So you can, much faster move on and say, just try to vectorize this in query. So a quick slide so you can see how it's done. You have the index annotation that has more meta information in the annotation about how you want to index and search a specific field. So in this type of index annotation, I'm saying this field, it's a vector field. Because normally I auto-detect the type. If it's a string, I do something specific like a tag. If it's a number, I do a numeric search field. But for a byte array, you have to basically tell it, I want this to be a vector in the search engine schema. I'm giving it the algorithm that I want to use and the vector type. All those things, I'm trying to come up with sensible defaults so the annotation reduces in size, and it does the most common thing first. The dimension, also it's something that you can potentially infer from the data in the model. So for now, you have to specify it, but pretty soon I'm going to get rid of it. The distance metric, in this case L2 of that's that internal product one, and the initial capacity. And all those things, we can probably come up with very nice sensible defaults, so it reduces the size. So that creates the index based on a blob of bytes. Now, the one above, vectorized, says I'm going to, the string image resource points to an image somewhere. Use the resource loader in Spring, find me that image, turn it into a byte array, run it through the embedding process, and put the results in the destination field, so on the image embedding field below. And so that's all you need to do vectorization and that becoming searchable. 2 annotations in your Spring model. So let's take a look at the application. And for this, I preloaded something like 100,000 or 11,000, I can't remember, images. So I'm going to run that Redis instance that has that data already, because otherwise we'll be here for a while. The vectorization process happens on save, but you can also do it in bulk. But when you do it on save per model, then obviously it's a much longer process. So not suitable for presentations. So let me now switch to, Oh, here we go. Okay, so I believe this is, yep, we're good. So you should see this running, and at some point down here, it will tell me, yeah, so there's 11,637 celebrities available. So if we go now to the browser again, and back to 8080, so I have now my celebrity match demo. So the future of this demo is that I'm gonna basically enable the camera, but I am afraid of what celebrity it's gonna come. Maybe I need to lose some weight first and then I'll do it. Okay, so let me choose a file. And I have so this is the actual data that was used for the training. So let's just pick one of those right now. So I don't know who that is. It looks like Gary Oldman, maybe. Looks too small here. And I'm also not showing the image right away, but when you do vector similarity searches, the same image, if it's the same vectorization values, that will be the first match. So we should be able to see who was that I picked. So remembering here, I'm going, oh yeah, it was Gary Oldman. So I'm basically taking that image and doing facial detection on that, trying to find where faces are. So that takes some CPU cycles. But then I grab the face, so those face markers that we saw in there, I grab that face and then I open that up a little bit so I can get more, because typically the anchor points are the eyebrows and the chin and I think the ears. So I take that and I open it up a little bit so I can get a proper portrait, and then I vectorize that and I do the search. If we look at the database, I'll show you how this looks. Actually, let me do it again, since yeah. So the Redis Insight, which is this GUI, has a profiler that allows you to basically see what's going on. So I'm going to do the search again. Let's see if I can close this one right here. Well, and if you see the keys that we have in there, we have, oh, yeah, I have to reconnect because I killed it and I started a new session here. But here, let me just show you the data running. Oh, and here's an example of one of the hashes. So if you look at one of these hashes, you can see that I have the image resource. It's in this case a class path, but it could be a URL or anything. Obviously, I didn't want to go outside the network to get the images. They're locally. But there is the IMDb ID, and then here's the image embedding that was generated. Obviously, there's not a proper viewer for that in here. I think we might do something about that at some point. And then there's a value for popularity and the name of the person, obviously. Yes, that's a byte array, yes. That's a byte array in Redis, so it would be a little Indian store. Okay, so let me do the search again. I don't have a back button, so just say refresh. Let's pick another one in here. And if you look at the application, I'm printing out basically the matches. So found 6. So I'm doing, this is k nearest neighbors. So it's doing k equals 6. So I can find 6 people that match the initial image, including the image itself, if it's found. And it gives you a list of values in here. Now, facial recognition with this specific model, this is a very generic model, but it's pretty good. But it matches on things that sometimes as humans, we will say that's not similar. It's looking for things like cheekbones and how deep your eyes are set, and obviously nose shapes and head shapes and things like that. But other things too that we might not consider as criteria for us to say this face, it's similar to this face. And now if we look in Redis, obviously it has to pass the input blob as part of the search query. But if you look at above, here's the FD search command that basically, that does the search. Now, let me show you in the code what that looks like. In the code, you don't have to do any of that crazy command to basically be able to do your search. The query, it's right here. So I created a stream-like API in Redis on Spring that allows you, I call it entity stream, for lack of a better name, and allows you to basically do a stream-like method chaining to basically query Redis. So in here, you can see that I'm doing a entity stream against the celebrity class, filtering by the image embedding using the k nearest neighbors with k set to 6 above, passing the embedding as byte array, which is what we grabbed from the input image, using the same code that we use to detect the faces and extract it. I limit it to k. This is a little redundant, but it's part of the query. And I collect that to a list. And then I loop to the list and print those. And in my template, my HTMX template, which should be right here, on this fragment, all I do is basically loop over the celebrities and get the image, the name, and the popularity value. So if we go back to the code, you can see now that I have Christopher Lee. Oh yeah, old school. Jack Palance. So that is how vector similarity search works in Redis. We have 4 minutes. I could show you one more demo, or we can do questions.
Questions. What are some of the performance metrics when you do this search? I mean, just doing an embedding search between for 11,000 something embeddings that you generated. What does the performance look like?
I don't know. In most cases, it's pretty damn fast, but it depends too. Typically, in a search like this, the generation of the embedding for the input is what it's costly. So if you already have, if you have the image already in place, it's super fast. Obviously, it is affected by the amount of data. Yeah. So it's not linear, but it's it's like n log of n or something like that. I can't remember the big O, but.
Some similar problem that you're trying to solve is like text embeddings that you're generating, trying to do a similarity search on 10 million records.
Yeah.
And I was just curious if there are some benchmarks.
Well, given the fact that it's all in memory, so first of all, obviously you need to be able to fit your data in memory for Redis, because one single Redis node needs to hold that data to be able to query it in completion. There is, obviously, if you get into Sentinel or Redis Cloud, we distribute the search and aggregate the results for you. But the more nodes, the more distribution of the data, the slower it's going to be. You still have to kind of query everywhere and then aggregate the results and give them back to the client. In general, it's I think there's Milvus is one of the fastest vector databases out there, and I think we're in par with what they do. So they do have more similarity metrics and more toggles that we don't have yet. But Redis, typically our approach is, let's do the fastest thing that can possibly be done because they're known for speed. Obviously, in Spring, you're going now through an ORM layer. So sometimes you can blame me for slow code. This is a very beta-ish code. We're at 0.8 release. Once we get to 1.0, it will go through a battery or performance test. So it's in par with the Redis philosophy of make it scream.
I'm assuming if you have a structured data and use the graph, Redis graph, that will be much faster.
Yes. Redis graph, it is the fastest graph database out there. That one I can actually speak on its behalf. But you have to be able to fit your whole graph in one key. So that's the downside of it.
So the matching itself happens on Redis.
On the Redis side, yeah. The JVM is just saying, here's some bytes, go find me something similar to it. Yes? The demo, it's on GitHub, but it's on the unpublished version of the library that I finished last night. I told you, this is conference-driven development. So it would be 0.81 proper, once it's out there, yeah, it will be ready to play with. And the demo is already there on my account, but I think there's, let me see. I believe, oh, there's also this other demo. It's part of the library too. There's a demos folder in the library, so there's a more comprehensive Similarity search on products that basically, but this one doesn't use input from the outside. This uses the images itself that are in the database to do the search, so it's super fast. So in conclusion, we're late already, but you have all the tools you need as a Java developer, as a Spring developer to do this. You don't need to write Python scripts in Jupyter notebooks to get this going. And you don't have to become a data scientist just to be able to do this. Here are some of the links. But I will give Pratik all a PDF of this so he can put it out there. Thank you, guys.